All right, back from break. Let's take a look. We looked at 4 problems here from this midterm 2 sample. Let's look at a different midterm from a different year. Again, 4 problems, A, B, C, D stuff going on here. And, well, let's go ahead and get started. So in problem 1, this looks like from chapter 8, 7 and 8, mostly 8, where we're looking at potential energies and conservation of energy. So we've got an elevator and the cable breaks. And the elevator is 1,300 kilograms. And the elevator drops like 30 meters. So this is like, you know, a 10-story building or something. 8 or 10, you know, something. 8-story building maybe. And it drops. Now, at the bottom of the elevator, they have built a safety device. So rather than building in the automatic braking system, which elevators have, and they're very safe, and elevators fail, but they don't fail catastrophically. At least that's very, very unlikely. I know that's always a risky thing to say, but there's a spring at the bottom of this one, and so the idea is they're just going to let you bounce off the bottom. Now, let's take a look at the diagrams here then. So here's the elevator at a height of 30 meters. So it's h is equal to 30 meters, right there. So here we are, 30 meters above this big spring, down at the bottom of the elevator shaft. And that's picture A. Now at picture B, the elevator has fallen. Now we're treating this as if it's in free fall. So there's no friction along the sides, it's frictionless, none of the braking system is working, and it's just free falling for 30 meters. That means by the time we get to picture B, the elevator's moving really fast, right? The elevator is going to be going fast, and what's going to happen is it's going to compress the spring, and that's going to be by some distance x. So h is from here to here, and then x is from here to here, and it tells us, I hope it tells us, yeah, the spring compresses by 3.5 meters. Now let's think about that. You're in an elevator, you've undergone free fall for 30 meters. I guess that means you're kind of floating around on the air, and then the elevator comes to a stop over a distance of 3.5 meters. Is that a good thing? Is that going to be safe? Let's see what the numbers are. Now the first thing they ask about is, they say calculate the kinetic energy and the velocity of the elevator in picture B. So you have fallen for 30 meters. That means you've taken potential energy, mgh, that's a certain amount of potential energy, and that has all been converted to kinetic. So I probably, you know, add a step here. The kinetic energy is going to equal to the delta U, which is mgh. It says the elevator now, it's moving at a good speed, and it has 382,000 joules of kinetic energy. Now, to find the velocity, we can take 2k over m square root, and it tells us that the elevator's going 24 meters a second. This thing is going 55 miles an hour or something like that. So at 55 miles an hour, and we're going to have you stop in 3.5 meters. We'll see. Now, in part B, it says, from this information, calculate what the spring constant is for that enormous spring down at the bottom. And I'm guessing the spring constant has to be pretty large, because it's got to be able to support an elevator, right? Anyway, what we can do is say that the energy is now entirely stored in the spring. That would be 1/2 kx squared. So all the energy is being stored in the spring. Now, what energy was there? And we can make a direct comparison between picture A and picture C. In picture A, I have an object at some height, and in picture C, I have a spring compressed. Now, the difference in height between the two pictures is actually h plus x. So it didn't just fall a distance h. As it compressed the spring, it continued to drop. Now that's additional gravitational potential energy. So I'm going to take all of that gravitational potential energy, mg, times h plus x, and set that equal to the energy now being stored in the spring, and then I'll solve for k. So I did a couple lines of algebra, put the numbers in. It looks like the k value is coming in right around 70,000 newtons per meter. So 69,680 newtons per meter is the spring constant for that. And that's what they wanted us to come in and calculate. Now, the next question they ask is, what's the largest acceleration that the elevator experiences? And we have to decide, well, what point are we looking at? Because when the elevator was in free fall, here, it had an acceleration of 9.80 meters per second squared. That's a pretty large acceleration. But notice that it slowed down and stopped over a much shorter distance. So I think the largest accelerations that the elevator experienced is somewhere here with the slowdown. Now, if we take a look at the force diagram, here we are slowing down. So the elevator is still moving downwards. There is a gravitational force of mg, and there's an upward force of kx. Now the mg is just constant. So that force isn't getting bigger, it's not getting smaller, but the kx force is. So whenever x is the largest value, that's the time at which the acceleration will be the very largest. So I guess the largest acceleration would come right at the bottom when v is equal to 0 and x is at its maximum value. So x at that point is 3.50 meters, and we can calculate the acceleration at that point as kx minus mg divided by m, and that worked out to be 178 meters per second squared. So that's a large acceleration. That largest acceleration right there is at 18 g's of acceleration. Now, so people, I guess people survive that. You probably break some bones or something. That's a really large acceleration. Let's see. Is that the end of the problem? And it is. It's the end of the problem that we have to look at. But is that what's going to happen if this spring is fully compressed with a spring constant of 69,680? Does the spring just stay compressed? And you go, no. If you actually did drop an elevator from 30 meters and it dropped and hit the spring and compressed it, the spring would then push back and it would shoot the elevator back up. Now, assuming there's no frictional losses anywhere, which is unlikely, but assuming no frictional losses, it would shoot the elevator right back up to 30 meters. And so this thing would just keep dropping on the spring and keep being shot back into the air or back up into the elevator shaft. So that's another thing to watch for. I guess what you need is when the elevator has stopped, some locking mechanism stops the elevator from getting shot back up, because that seems dangerous. Or instead of a spring at the bottom, put something at the bottom where the spring breaks, or so there's nothing to shoot the elevator back up. Sounds kind of dangerous with if the elevator gets shot back up through the elevator shaft. Or maybe it sounds like a ride at Disneyland or something, right? So maybe that's the new ride, the elevator ride. All right, let's take a look at problem 2. So in problem 2, we have an automobile, one of our favorite objects, and it has a power of, what are these horsepower? Okay, anyway, the car has 140 horsepower. Apparently a horsepower is 746 watts, so I'm going to get that converted right away. So I never wrote down horsepower over here. I just converted it. So the power of this car, its maximum power, is 104,440 watts. The car is 1,100 kilograms, is what they told me. So I'm making sure I got the right numbers here. There is, okay, this is weird too. So it says that we have a coefficient of friction 0.30, but they're calling it rolling friction. I don't care for the word rolling. Maybe I should have edited that out. When they say something like that, whenever they say there's a coefficient of friction, the intention is for us to take the frictional force and represent it as a coefficient times the normal force. So I'm going to use that same approach and say that the frictional force then is mu times n. And the car's on an incline, and so from the force diagram, I can see that the normal force is equal to mg cosine theta. I can substitute that in. Now, they tell us to draw a diagram showing all the forces. That's always good advice. So let's take a look at the diagram. So here's this car. It's headed up the incline. Now, it says that we're going at a constant speed. So in part B, it says, what's the maximum constant speed at which the car is able to climb the hill? So the idea is, you hit the accelerator pedal, you're right at maximum power, and you start picking up speed, but then you top out. So there is some speed at which you top out, and at that point, you're traveling at a constant speed, the acceleration is 0, and that means that the forces are they're actually balanced. So n and mg cosine theta, they equal each other. Now, in the incline direction, there is a force, I'm calling it capital F, and that is a frictional force between the tires and the pavement. Now, that force, big F, is coming from the engine. So, the engine is the crankshaft, the engine is creating this rotational motion, and that's being transferred to the tires, and then the tires are gripping the pavement, and that sets up frictional forces, static frictional forces, and that's what pulls the car up the hill, is the grip of the tires. So I am going to put in a subscript on that power of the car and saying that power goes to force big F. Okay, capital F is the force that power is associated with. The power is not going into gravity, the power is not going into normal force, it's not going into friction, it's going into that force that's pulling us up the hill. So that force, big F, needs to be as large as mg sine theta plus the frictional force. Now the frictional force, we said, could be represented as a coefficient mg cosine theta. So this is how big the friction, the force of the tires gripping the pavement, pulling the car up the hill. This is how large that force needs to be of the pavement pushing the tire forward. It needs to be equal to 4,160 newtons. So that's the force we need to go up the hill at a constant speed. That's enough force to offset gravity and offset the friction. Now, where we're headed with all this is that the power is going to be related to the force and the velocity. So it's specifically the force pulling the car up the hill, and the speed is what we're solving for. So we can take this formula, again, this is derived in class. V then will depend on the maximum power of the car. This is the maximum speed, which we can substitute in 104,440 watts divided by the force. These need to be standard units. 4,160 newtons, and it says the fastest speed at which this car can climb this hill would be 25.1 meters per second. That's pretty good, right? 55 miles an hour or something, 55, maybe 60 miles an hour, something in that range. And we are headed up this incline of 5 degrees. Okay, I exaggerated. that angle is much larger than 5 degrees. In this case, the reason for having the angle larger is to be really clear about the components of the gravitational force. All right. All right, that's it. That's part B. And so C says, now how much energy has been transferred by each of the forces acting on the car during the 800 meters. So it's an 800 meter hill, not height-wise, but length. So we have to travel 800 meters to get to the top of the hill. So again, this is going back to chapter 7 and saying a perpendicular force, which would be N, or maybe mg cosine theta, those are perpendicular to the displacement. They are not transferring any energy. So those I can immediately set equal to 0, and I can get points for that. All right. And then, let's see, the work being done by the force, F, associated with the engine, is big F times D, and that worked out to be 3.3 million joules, and I put a plus sign on that. That energy is going into the car. That will end up as one of a couple things. It could end up as potential energy as it climbs the hill, or it can end up as kinetic energy. All right, so let's keep track of what happens to this energy. Now, work is also being done, energy is being transferred by mg sine theta, but as you can see, mg sine theta is opposite the direction of displacement. Mg sine theta is taking energy out. So now I can calculate that as mg sine theta times d. I put a minus sign here, but then on the other side I switched and put the minus sign out here. Anyway, the amount of energy taken out by the gravitational force is 0.75 million. Now, I did everything in terms of millions so that I could do an easier comparison with the energy transfers, is the idea. So again, 0.75 versus 3.33. So I put all this energy in, that's coming from the engine in the car. This much is being taken out by gravity, and that's because I'm climbing the hill. Now, the gravitational energy, that's going to be potential energy of the car. The car is actually climbing to a higher and higher elevation, and of the 3.3 million joules we put in from the engine, 0.75 million are going to get stored as gravitational potential energy. So if I need to go downhill, I could get that energy back again. Now, the other force that is taking energy out is friction. And remember, friction is given by mu mg cosine theta. And so we can write the energy transfer as mu mg cosine theta times d. So kind of a trick we're using here, and we did this in the other examples when we introduced this back in chapters 7 and 8, but mostly 7 for the work calculations. If I can take all my forces and divide them up into components that are either perpendicular to displacement, right? Well, the perpendicular ones just don't transfer energy at all. And then I can look at the ones that are directly aligned with the displacement, the same direction. Those are going to be positive. And then the components that are exactly opposite displacement, those are going to be negative. And then I don't have to do any integration. I don't even have to use the dot product formula. I can just calculate it as force times distance, force times distance, force times distance. Okay, so that's certainly a way to go in and solve these problems. Let's see. So I plugged all the numbers in for the frictional losses. Oh, look, that's where we're losing most of the energy. What is this? This is like 75, 80% of the energy is being lost due to frictional effects within the car. So I don't know what this rolling resistance includes. In some cases, they actually think of it as including air resistance, resistive effects within the car itself. The car's not frictionless when it rolls. Anyway, according to the numbers given, most of the energy, again, 75–80% of the energy is being lost due to friction, whereas 20–25% of the energy that the engine is providing is being stored as gravitational potential energy. So those are the two places the energy is going. The W net is 0. Okay, now that means that the energy we're putting in is all going somewhere else. None of it is going in to speed up the car at this point. We're already topped out we're already tapped out at that high speed, and so the delta K is equal to 0. Now that doesn't mean K is equal to 0. It means that we're a constant velocity. All right, so again, it's another good example of kind of energy bookkeeping, which forces are transferring energy in, which forces are transferring energy out. Questions on that? All right, problem 3. Now this, we are looking at a bullet striking a block of wood on a horizontal surface. Now when I read these problems in textbooks, I always think, I don't think that's very realistic unless, let's see, here is a block of wood. Here is a bullet coming in at, 1,000 meters a second or something, or 400 or 500 meters per second maybe. It hits the wood, and the wood just is stable and slides along the surface. I don't know about that. I think the wood block would have to be anchored into a track, maybe. Maybe that's how this is done, because apparently these are how ballistic tests are done. You fire into some object and you find out what effect that has on the object. So again, I think the wooden block's going to need to have something. Again, maybe it's got something where it's on a track and it is constrained so that it slides along. So anyway, we're going to have the bullet hit the block, becomes embedded. Now that's an inelastic collision. Energy is not conserved. Kinetic energy is not conserved. Some of the energy, maybe most of the energy, is going to become thermal, and so we're going to use momentum conservation, not energy conservation, for that first step, for the collision itself. So that's momentum conservation. And then once the bullet has hit the block, then we move into step 2, where it says that there is some kind of a frictional force slowing this object down. It travels a distance of 9.50 meters. The mass of the bullet was 15 grams. The mass of the block, 2.10 kilograms. I gotta make sure I get everything converted to kilograms there. And then the kinetic coefficient of friction, 0.25. So those are the formulas I'm working from. They want us to work back and find out how fast the bullet was traveling when it came in, when the bullet was traveling initially. So I'm going to need both of these equations. I know D. I've got a coefficient of friction, so I can calculate friction. Friction is going to be given by mu sub k times n. And n is going to be the same thing as m plus m times g. So I have substituted in this for the frictional force and times d, and then the kinetic energy right after the collision. So right after the collision happens, there's going to be a kinetic energy 1/2 m v squared. Now the mass in this case, it includes the bullet and it includes the block. And for the energy formula, the m's will cancel. And if I solve for v, v is 2 times mu times g times d square root. And again, the mass is canceled out. I've got to take a square root. And plugging all the given numbers into this, I ended up with the speed of the block immediately after the collision has taken place is 6.82 meters per second. So now that I've used the energy formula, I can go back and use the momentum formula. So what happens here is the thing gets fired and then it slides. Now all the information we have is at the end of the problem, and then we have to work our way back through to the beginning. So I know what the numbers are at the end. I got to work back to the beginning and eventually solve for V naught. So from the momentum formula, V naught is given by m plus m over little m times v, and putting the numbers in there, I get 962. So it was near 1,000 meters per second. So that's a really, really high velocity for this projectile. 962 meters per second. Okay, momentum conservation is in there. Energy conservation is in there. All right, questions on this problem? Now following up with B and C and D, these are all energy questions. So this, as we were saying before, the energy that the projectile, the bullet, has before the collision is 1/2 m v naught squared. And so I know all those numbers now. I know the mass that needs to get converted to kilograms, and I know the V naught. Putting all those numbers in, I end up with a beginning kinetic energy, 6,940 joules. Now, after the collision has taken place, the kinetic energy formula is going to become 1/2. They're both combined, m plus m, little m plus big M, times the lower speed. And that says right after the collision, we have 49 joules. Right before the collision, we had almost 7,000. So you can see how much thermal energy. Did they ask for that? Anyway, you can see the numbers. So let's see, was kinetic energy conserved? No, it's an inelastic collision. And what happened to the energy? The energy went thermal. How much energy would that be? Well, it looks like 6,891, something like that. So of that 6,940 joules, we only lost about 50. Okay. Or I'm sorry, we only kept about 50. Almost all of the energy was lost in the collision. So lots and lots of thermal energy in this example. All right, questions on that? So good, a couple of energy problems, 7 and 8, asking different aspects. I feel like these problems are covering a good number of the topics within each chapter. And then a momentum and energy problem here. Ooh, we got to have something with rotational motion. So let's look at our rotational problem. So this one, you just have to see how it works out. This one only had one question on rotation. The previous set of problems we looked at had a couple problems with rotational motion. It could go either way. Oh, maybe the earlier one. What was the earlier one? Oh yeah, it was only one, huh? So I should point this out too as we head into this last problem. So we could easily have two problems on rotational motion. It could go either way. So at the end of the semester, I kind of take a quick look through the midterms that we've done, and I look for things that maybe weren't covered quite as much, and then maybe I'll come up with a finals question that will cover an area that we missed with the earlier midterms. Now, these midterm reviews are going to be good when you're preparing for the final. I'm looking too far ahead here. But these are good to come back and review at the end of the semester. But also think in terms of what kind of examples maybe are missing. Are there things that we've looked at in class that weren't covered as clearly on on the final, and you guys are, you're allowed to ask me questions. I probably won't tell you what's on the midterm or what's on the final, but you guys can ask questions, and if there's something I can respond with, I will do so as far as what the coverage on these midterms might be. All right, but again, be prepared. There could be a couple of problems on rotation rather than just one of each of these. So take a good look at those rotational chapters. All right, here's the last problem then from this second set of problems. And it's saying that we just have a cylindrical disk, and we're rotating it around the center of mass, and we're going to accelerate it from 150 RPM to 300 RPM. Now, if you remember, RPMs are revolutions per minute, so this would be 300 revolutions per 60 seconds. And then I'm going to go ahead and put everything in standard units. Now, that you don't necessarily have to do that for some calculations. For some you do, for others you don't. And so this is one of those situations where putting everything into radians per second, those are standard units, and that means they'll work in all the formulas that I run into. And so I am going to go ahead and convert. So the omega naught becomes 31.4 radians per second, and the 400 revolutions, RPM, becomes 41.9. So that's the speed at first, and then we go through a period of acceleration where we increase the rotational velocity to a higher value. The radius here is 0.35 meters, the mass is 10 kilograms. Here is my kinematics diagram. That's the direction of velocity, that's the direction of radial or centripetal acceleration, that's the direction of the tangential acceleration, this is the direction of omega, that's also going to be the direction of the rotational acceleration. And in the first part A says, what is the angular acceleration? And I can get that as omega minus omega naught divided by the time. So there was a 4-second period, they tell us, during which the acceleration took place. Now what I can see is during that 4-second period, the omega increased from 31.4 to 41.9. That's an increase of 10.5 radians per second, and that's giving me a rotational acceleration, or an angular acceleration, of 2.62 radians per second squared. Now in part B, it says come in and ask about, or calculate, radial and tangential components of acceleration. So the angular accelerations are in radians, those are angular, but now we're looking at the components of linear accelerations, and by linear we really mean something measured in meters per second squared. So the tangential acceleration of a point along the edge would be, that's what they're asking about, something right along the circumference, would be r times alpha. R right along the edge is 0.35 meters, multiply that by the alpha value, 0.916 meters per second squared. So again, a point on the edge is going faster and faster, and it's going faster and faster in terms of its linear velocity by 0.916 meters per second per second. Now what about the centripetal or radial acceleration? Well, that could either be v squared over r, or equivalently r times omega squared. So I'm going to use that. I already have the omega, so plugging numbers into this formula, now I didn't write it out explicitly, but plugging numbers in, I got 345 meters per second squared back when we were doing 300 RPM. And then at 400 RPM, that jumps from 345 to 614. The radial acceleration is going to depend on omega squared. So an increase in omega, I get an extra boost from squaring the omega in that formula. So you can see the radial accelerations are really quite large. So we have really large values for those, and those are going to be in meters per second squared. And they're even though the angular acceleration is constant, that doesn't mean that the omega is constant. It means the omega is increasing, and that the radial acceleration will also be increasing. So that was something expected in the problem, is that students would make some kind of a comment about the radial acceleration is not a fixed value, and then one resolution for that is to write down what the radial acceleration was at the lower lower spin rate, and then at the higher spin rate. Last part C, what is the net torque acting on the cylinder? So we're told that this is a cylinder, and it's got a mass of 10 kilograms, it's got a radius of 0.35 meters. That's enough. I can go in and calculate a rotational inertia. Now, the acceleration that's happening is happening as a result of a torque. An object spinning doesn't just spin faster on its own. We have to apply some kind of a torque. And so we can calculate the amount of torque needed would depend on how much rotational inertia, how much rotational mass the object has, times the acceleration that we want it to accelerate at. So the rotational inertia can be calculated as cm r squared with a shape factor of 1/2 for the cylinder. That gives me a rotational inertia of 0.613 kilograms meters squared. And then to calculate the torque, we take that rotational inertia and multiply by the rotational acceleration. It says that we would need a torque. It's not a very large torque, 1.60 newtons per newtons times meter. Sorry, the torque is going to be in newtons times meters. All right. Okay. Everything checks out. I'm not seeing any numbers that look crazy. As always, if you find errors, let me know. If you have questions, let me know. But that wraps this up. So good luck with the preparations for the upcoming midterm. Again, our mascot, Laney the Eagle, is here for the midterm reviews. I've got office hours set up, plenty of office hours, so stop by and let's get those questions looked at.